Hi! In the previous video, we talked about carbon hybridization and we've learned about the different hybridization of carbon, which are sp3, sp2, and sp. Now it's time for us to investigate further real organic compounds, and let's talk about further about sigma and pi bonding. These two types of bonding that exist in carbon, depending on its hybridization, will explain to us what's going to happen to those that are hybridizing and those that are unhybridized. So let's look at three compounds today so that we'll be able to learn about sigma and pi bonding. Let's start with ethane, C2H6. Now, when we draw C2H6, remember that it's just carbon and hydrogen. We know that there are two carbon and six hydrogen. So that means that carbon to carbon will be side by side because hydrogen has to be on the sides always. So when we draw the structure of that, it's going to be C to C will be together and there will be six hydrogen. Now remember, carbon has to have four. You know the reason why it has to be four, correct? So we'll start with all single bonds. If I have to connect carbon to carbon, then that will be single bonds. And so if there's already one single bond from carbon to carbon, that means I need to supply three more for each carbon to complete the four so that it will be eight. And considering that, that means I've already supplied all the six hydrogen here. So that means I'll put H, H, and H here, another H, another H, another H. So this is the complete structure of your C2H6 ethane. So when we look at these leads, now we have to look into the orbitals. What's going on in the orbitals and what type of hybridization is present. Now, if you look closely, ethane, carbon has all four single bonds, and so it has shared four times. If it has shared four times, that means its S1P3 for carbon will all be shared to all the S of your hydrogen as represented here. So the 1s1 of all hydrogen will all hybridize with the S and the P3 of carbon, each of the carbon. So that's what happens actually. So in C2H6, it's just plainly an sp3 hybridization because you have four coordination numbers as represented by this. So you have 1, 2, 3, and then 4. So all the four orbitals of carbon have to be shared. So in this case, if it's all being shared, we call this type of bonding sigma. Okay, so take note of that. It is sigma. So now, it's time for us to shift to another compound. Okay, let me proceed to the next compound. Next compound is this, ethylene. What if we have C2H4, not C2H6? What's gonna happen to our structure? C2H4 is being drawn this way. It's still C2, so two carbons, but it is just reduced now to four hydrogen. What's gonna be four hydrogen? Of course, you just need to supply four, so that means you have 1, 2, and 1, 2. If that's the case, carbon will have two hydrogens each. That means each carbon will have two more. So that means your carbon to carbon is a double bond to make your carbon supply or meet the octet rule. So C2H4 now has a double bond. Now let's look at the hybridization. What's going to happen? Because if you look closely, carbon will just hybridize three times. So because it has three coordination numbers, 2H and 1 from C to C. So three coordination numbers, that means only one S and 2P will participate. If that happens, there is another P that doesn't participate. Now, the other one that is unhybridized will be the one to form what we call the pi bond, while the rest will be sigma bond. I told you previously about sigma bonds. The sigma bonds are the ones that came from the hybridization of your orbitals. Now, it so happened that in ethylene, one will be unhybridized because of the presence of the double bond, because you have a reduction of the number of coordination numbers. So instead of 4 a while ago, we had 3. So now that we have 3, that means 1 from the P will remain unhybridized, and the effect of this is that you will get what we call the pi bond. The pi bond is formed from unhybridized orbital, while the rest will have sigma bonds. So if you will count in C2H4, how many sigma bonds you have? You have 1, 2, and 3. And how many pi bonds you have? You have 1 pi bond. So if you have a double bond, then one of that will be a sigma bond from the hybridized orbital, and the other one will represent the unhybridized orbital, which represent your pi bond. So that's what happens when you have unhybridized orbital. There is what we call a pi bond. So let's now proceed to the next one. Now the next one is a complicated compound, which is, sorry, let me hide the tool. That's going to be acetylene. It's now C2H2. From C2H4, it became C2H2, the more reduction of hydrogen. So when we draw the LEDs of that, it's going to be like this. C2H2 will have triple bond from C to C because you can only supply 2 hydrogen. 2 hydrogen each, that means each carbon will lack 3 more. So that means you have a triple bond. In this case, your coordination number is 2, 1 on each side. So if it's a 2, what's gonna be your hybridization? It's just gonna be an S and P because you just need two, one from S and one from P. So you can already guess that P has remaining two that are unhybridized. So in a triple bond, then, if you have this structure in a triple bond, one will hybridize, the other two are unhybridized. So if we will see how many pi bonds you have what we call two pi bonds that will form. So you have two pi bonds that will form. And since you have two hydrogen here on each side and one here that hybridizes, so that means you have three sigma bonds all in this structure. So three sigma bonds come from each CH and the C to C hybridization, and the other two pi bonds will come from the other two bonds that came from the empty or unhybridized remaining p orbitals. So generally, if you get a P, just one P, an SP, you get a triple bond. An SP2 a while ago, you'll get only a double bond. And if it's an SP3, then you will get what we call a all sigma bonds. So that's it for carbons hybridization. So if you will look at the summary for this, you will see this. So sigma bonding will occur when you have head-to-head overlap of hybrid orbitals, particularly hybrid orbitals, sorry for the unhybridized. So all single bonds consist of sigma bonds, and one of the double bonds or one of the triple bonds is always a sigma bond. And pi bonding, it's always side to side overlap of unhybridized p bonds, and it contains two electrons total because they just, you know, interact with each other. So the second and the third bond of a double or triple bond are always pi bonds, and pi bonds can only occur when central atom is sp or sp2. It will never happen or present, it will never be present if you have an sp3, just sp or sp2 hybridized compounds. So let me just end up with this benzene structure. You know, benzene, it's a C6H6, and you usually draw it like this, and a hexagon with a circle here. So that's an alternating double bond. That means if we count how many pi bonds we have, it's three pi bonds because you have three double bonds. And that pi bond, because it's alternating, that means they exhibit resonance structure. And when they exhibit resonance structure, that means your electrons are delocalized, so they're just traveling around that cyclic structure. So that's why we draw it like this. So that's it for now. I hope you learned from this. Watch out for the next video. Bye.